All right. This zeroness actually has a very significant interpretation. Is that if I treat the bilinear form A as a as some kind of inner product, right? So you can easily imagine that the property of an inner product is actually the same property as that of a bilinear form. An inner product between two vectors, right? They are bilinear, right? So if you scale one vector by a factor of 2, the inner product is scaled by a factor of 2, right? And it's also linear with respect to each of the components. So it's actually very normal to actually treat the bilinear form as some kind of inner product. And if you consider this bilinear form as a special kind of inner product within the functional space, then what this is saying that the inner product of the error and the entire XH space is equal to 0. Okay, so what does it mean by a vector, for example, having an inner product to any vector within the space? It means that vector is orthogonal, right, to that space. So you can imagine, let's say XH is the blackboard. It is any vector in the blackboard. Then UH minus U having a 0 inner product to any vector in the blackboard means basically U minus UH is orthogonal to the blackboard. And also in particular, UH is actually one element of XH, which means UH is on the blackboard, right? So that means U, the true solution, has to be somewhere, if you draw a line from UH, the finite element solution, and draw a line orthogonal to the blackboard, the true solution U has to be somewhere on that orthogonal line. All right. So basically, let me draw this. So let's say this is like a blackboard. The surface of the blackboard is XH, and if I have solved for a finite element solution, let's say UH, then I draw orthogonal line, then U has to be somewhere over here. Okay? Okay, what that means is that if you were trying to find another arbitrary function in XH, so if you try to find anything else in XH, the distance between that something else to U has to be longer than the distance between U and UH. In that sense, UH is optimal. So UH is the closest thing you can find to the true solution within that subspace of XH. Right? So that's a qualitative argument, and mathematically, of course, you can show the same thing, which means the A of UH minus U, UH minus U. So this is like the square of the distance if you treat the A as an inner product, has to be less or equal to A of any W minus U for any W within the XH. And it's just the algebra to figure that out once you know that, right? So basically you can expand the proof is really just to expand the U minus H as W minus U as W minus UH plus UH minus U, right? You can expand these and then use the bilinearity of A to expand the right hand side into various terms, and it's easy to figure out the right hand side is just the left hand side plus something that has to be greater or equal to 0. All right. Okay, so this is saying that the finite element solution is optimal. but it's optimal in a very particular sense. It is optimal, for example, for the Poisson's equation. It's optimal for this, right? It's optimal in the sense that the distance defined by the norm of the gradient is going to be the smallest. So how do we translate this into other norms? Well, so in order for you to translate into the other norms, you have to use some equation-specific analysis. For example, for the Poisson's equation, there is actually a relatively easy way to translate the norm in terms of the gradient to the norm in terms of the just the function itself. It's called well, basically there is a theorem saying that the derivative norm has to be bounded by a constant times the norm itself. If you know the value of the solution at a fixed x0 is equal to 0, right? And this A would actually dependent on the domain and x0. So this is a way to translate the so-called energy norm in finite volume, which relates to the differential equation, the bilinear form itself, to a L2 norm. Okay. And then this just says that the norm that is just says that by this constant A, this just says the finite element solution is close to the optimal. Okay, by a constant A. So how does that relate to the order of accuracy analysis? And then the order of accuracy analysis actually relates, involves constructing a particular function that is actually second order accurate or whatever order accurate. So that analysis is very similar to the one we just showed before. For example, if you have a function and my space is actually piecewise constant space, I can construct this piecewise linear interpolant, right? We can construct a function that just takes the nodal values and interpolate this function with linear lines. And we can show that the distance, the L2 distance between the interpolant and the real function is actually second order accurate. Okay? And once we show that, we know that the finite element solution is actually better than the piecewise linear interpolant we just constructed. Okay? So therefore, it must also be second order accurate. So this is kind of a general way of doing order of accuracy analysis in finite elements. It's actually a little bit indirect. You have to first use the optimality of finite element to say that the finite element solution is optimal in a particular norm. And then you have to relate that particular norm to a more general norm. And the third step, you have to construct a particular function that is not optimal, but it's to a certain order of accuracy. And then these three steps is going to guarantee that the finite element solution is to the same order of accuracy. Yes?
But doesn't it all come down to the truncation error that we make when choosing all basis functions?
It relates to the truncation error analysis. So you still have to do truncation error analysis to the particular function you construct, right? So here, for example, I'm using a piecewise linear interpolant, and you have to do truncation error analysis to see how different is the piecewise linear interpolant to your original function.
But that's the only point in finite element where we introduce error, right? So
we introduce error when we restrict the space, right? So the how good your finite element is basically relates to how powerful that space is. If you can choose the best function within that space, how accurate can you go? Okay. All right. So Wednesday's guest lecture, And next Monday is the last lecture by me in this subject, and Wednesday we'll have the project presentations. All right.